Hello everyone, hi, I'm Sweat Pearl Jean Ken Recitado. Today, we're going to explore something that might sound a bit technical at first. It's about equivalence relation and partial order relation. But don't worry, we'll use simple examples, visual and real-life situation to understand them. These two ideas help us answer a simple question. How do we organize things? Sometimes we group items that are similar, sometimes rank them from lowest to highest or simplest to hardest. That's exactly what these two kinds of relation help us do. So to understand equivalence or partial orders, we first need to know what a relation is. A relation is like saying this is connected to that based on some rule. A relation links to two elements within a set based on a specific rule or condition. So, for example, people who like the same hobby, that's the first example. The second example would be numbers that are bigger or smaller. The third example is sets where one is inside another, and the fourth example is students in the same grade level. All of these are ways of relating things. So a relation is just a rule that needs to tell us who is connected to whom. Once we understand that, we can classify relations into different types like equivalence relations and partial order. Equivalence relation or grouping elements. Now let's talk about equivalence relation or grouping elements. This relation create groups of things that are similar based on some rule. To be an equivalence relation, the rule must have three properties, which are reflexive, symmetric, and transitive. Reflexive is about everything that relates to itself. For example, 5 has the same remainder as 5. The symmetric, if A is related to B, then B is also related to A. Example, if you and I have the same birth month, then I also have the same birth month as you. Transitive, if A relates to B and B relates to C, then A relates to C. Example, if I'm in the same grade as Robert and Robert is in the same grade as Bia, then I'm in the same grade as Bia. When these three conditions are true, objects from equivalent classes, basically groups that belong together, we'll see this in the first example. So, partial order relations or establishing hierarchy. Partial order relations work differently. Instead of forming groups, they create rankings or orderings. But the order doesn't always have to be complete. Some things might not have to be comparable. A partial order must satisfy 3. Reflexive, antisymmetric, and transitive. Reflexive, everything is related to itself. Antisymmetric, if A is less than equal to B and B is less than and equal to A, then A and B must be the same. Transitive, if A is less than and equal to B and B is less than equal to C, then A is less than equal to C. A perfect example is the divisibility relation. We'll see how numbers can be arranged in levels like a family tree. Let's walk through our first real example of an equivalence relation. The problem is, define A relates to B if A and B have the same remainder when divided by 4. So if I divided numbers by 4, the only possible remainders are 0, 1, 2, and 3. That means we can group numbers like numbers that leave remainder 0, so 0, 4, 8, and 12. Numbers with remainder 1, 1, 5, 9, and 13. So remainder 2, we have 2, 6, 10, and 14. And the last class is the remainder 3. We have 3, 7, 11, and 15. Each group is an equivalence class. This group doesn't overlap and they cover the whole set. This is what we call a partition. The set is cut into perfect non-overlapping groups. Now let's try a partial order. We have the set B is equal to 1, 2, 4, and 8. We say A relates to B if A divides B. Think about it. 1 divides everything, 2 divides 4 and 8, and 4 divides 8. So, reflexive, yes, because every number divides itself. For example, 1 divided by 1 and 2 divided by 2. Antisymmetric, yes, because if 2 divides 4 and 4 divides 2, that would mean 2 is equal to 4, but that cannot happen, so antisymmetry holds. Transitive, yes, if 2 divides 4 and 4 divides 8, then 2 divides 8. So this is a partial order. When we draw the Hayes diagram, we get a chain 1, 2, 4, and 8. This shows a clear ordering from the smallest to greatest based on divisibility. Now, we have the real world classification, and this is about blending relations. Many systems leverage both equivalence and partial order relations to organize complex data or individuals. So the equivalence is grouping by grade level, and the partial order is ranking by academic performance. So in school, students are grouped by grade level, grade 7, grade 8, and grade 9, and so on. Everyone in grade 9 is in the same group. This is an equivalence relation. So the grade 9, where all members are considered equivalent for administrative purposes, this form clear and distinct sets. But inside each grade, students can be ranked by average to highest to lowest. This ranking is a partial order. So, with each grade level, students can be ranked based on their average scores or grades. This creates a hierarchy from highest to lowest, but not every student is directly comparable. For example, two students with different averages. Real systems can use both equivalence and ordering at the same time. Equivalence is equal to same group. Partial order is equal to rank inside the group. Hayes diagram for subset relation. Here's another partial order example using sets. We have a set called S, and it have 1, 1 and 2, 1, 2, and 3, and 1 and 3. And the relation is A is a subset of B. If we look closely, 1 is a subset of 1 and 2. 1 and 2 is a subset of 1, 2, and 3. But 1 and 1, 3 cannot be compared because neither is a subset of the other. This is why we call it a partial order, because some pairs cannot be compared. From the diagram, we can identify minimal elements like the 1 and 3. The maximal element of the set S is the 1, 2, and 3. This visual helps us understand how the sets relate like a branching tree.
So here is another real-world application like clothing. We group this by color. So here we organize clothing by color. All blue items go together, all black items go together, and so on. We're not saying one group is better than the other, we're just grouping the items that share the same characteristic. Equivalence relation. Same colors to same group. Think of it like sorting your clothes. Clothes are grouped if they share the same color. It's a way to organize items that are alike in a specific way. Forms equivalence classes. Each group of clothes, example all blue items, all black items, all white items, form an equivalence class. These classes are distinct and contain all items that are equivalent under the defined relation, which is the color. Focus, similarity, not ranking. The key here is finding common characteristics. We're not saying blue is better than black, just that all blue items belong together. It highlights shared attributes without imposing an order. Now we're done with the equivalence classes. Now let's proceed to partial order of the clothing. Now instead of grouping by color, we organize clothing by formality level. Like the casual outfit comes first, then semi-formal, then formal. This is a partial order because items follow a progression. We're comparing which clothes are more formal, not whether they are alike. Some items might not compare, like sportswear versus office wear, and that's normal in a partial order. Here, the key idea is that we arrange items by a clear ranking, not by similarity, direction, and progression. This demonstrates a clear hierarchy or sequence. Each level is a distinct and progresses in formality, but not all items at the same level are necessarily comparable. For example, a suit isn't more formal than a dress, they're both formal. Focus, progression, not similarity. Unlike grouping by color, here we're concerned with how items relate in terms of their level of formality, showing a path of becoming more intricate.
Now here is our key takeaways. To end our lesson, here is the big idea, or here is the main key takeaways that we have to remember. Equivalence relation helps us create groups based on similarity. For example, same grade, same remainder, and same color. Partial order helps us rank or organize things based on levels, like the divisibility, GPA rankings, or set inclusion, and also both of these relation helps us make sense of the world by organizing it. Sometimes we group, sometimes we rank, and sometimes we need both. And with the examples we explored today, you know how to organize and work with this. And with the examples we explored today, you know how to organize and work with these two very important concepts. which is the equivalence relation and partial order. And that's all, everyone. Thank you for watching this video.